Okay, class, this is the last 30 minutes of class that we or 25 minutes of class that we would have had if the power had not gone out. So um, this is the we went through all of that about eigenvalues and eigenvectors and how to find them and what they mean and how they're useful, at least a little bit. And so now, like I said, finding eigenvalues and eigenvectors by hand with 2x2s is important because on the final exam, you'll have to do that at least once to find the eigenvalues and eigenvectors for a 2x2 by hand. But most of the time, we actually, we find them using a computer, especially if they're bigger. But we need to talk a little bit about the ways that a computer can get it wrong or kind of mess up. So for instance, say I have this matrix A here, -3, 1, 0, -3. And so it's already been put in Sage for me. So if I do A dot char poly, that gives me the characteristic polynomial of the matrix. And then like if you don't want lambda, if you just want X, then it'll give you an X. So, but I'll keep it in lambda there. All right. And so then you can also have it automatically factored. So for instance, if you do FCP stands for factored characteristic polynomial. And so in this case, we get lambda plus 3 squared. Um, and so then you can try to solve that. Like that's if it's factored, you just know like lambda is -3. In situations where it's hard to factor or anything like that, you can always just like have Sage give you the eigenvalues. It gives you them in the form of a Python list, and it -3 is repeated twice, so you get it a list of it twice there. Okay, um, so notice like the eigenvalue is not distinct. Okay, so then I can always get the eigenvectors. So even though, and then this is not as nice of a showing, but I could say show this, and then I wonder, I don't know if this works or not. Yeah, okay. So when you show a list in Python, if you have like the star in front of a list, it sometimes means like open up the list. So showing the things. Um, so here in this case, the eigenvalue is -3. It has the basis for the eigenspace is the vector 1, 0. Notice there's only one of those, not two, and yet the multiplicity of the eigenvector is 2. So it comes in tuples like in three tuples like that, three tuples. All right. So now that was working with nice integers. But what happens if we're working with like a discrete linear system, like we had in the example from 4.1? Well, in that case, you'll have A like that. And so um, if this matrix right here, its eigenvalue is 1. But if I do A minus the identity matrix dot RREF, I don't get a null space, right? And that's because of how the computer has that floating point error that's so tiny that it doesn't affect us. But when you're trying to zero stuff out with reduced echelon form, it misses it and then ends up with like that. Okay, so that means you can't just use the computer step by step like you would by hand. There's other things the computer has to do to avoid this situation. And so to just use you want to use the built-in Sage functions. And so for instance, dot eigenvectors right will give you that. And let's do the show again. Star. So evaluate that. So in this case, we get two eigenspaces. The first one has eigenvalue 1 with the basis vector 1, 2, multiplicity 1. The other eigenspace has eigenvalue 1/10, eigenvector 1, -1, multiplicity 1. Okay, and so that's the method you want to use in Sage, and it's best if you can keep things as fractions because of how Sages does pure math sort of stuff, symbolic math. It's always nicer than if you have nice numbers, put them in as fractions, basically. So now let's show some examples of doing 3x3s using Sage. So here we have activity 424, where we did part B in class, part A and B in class, but then part C, D, and E were all 3x3 matrices that would have taken longer to solve. And they gave us the characteristic polynomial, so you didn't have to deal with factoring a degree 3 polynomial. But then you would have to find the null space for each eigenvalue. So for part C, you get a repeated eigenvalue of -2. Same for part D. And for part E, you get 3 distinct eigenvalues. So to do that in Sage, I took those 3 matrices and put them in Sage right over here. And so then I called them A1, A2, and AC3. Maybe I could have called them like AC, AD, and AE because they're parts C, D, and E of that activity. And then make sure if I make a change, got to make a change to everything. All right, so then what I'm doing is AC.eigenvalues right, and then AD.eigenvalues right, and then AE.eigenvalues right. So, the printing and the showing is coming up at weird places. Okay, so now if I change that back to show, and that to show, and that to show. All right, well, activity 424C, you see that here there's 2 eigenspaces, -1, with the basis for the eigenspace being 1, -2, 0, and having one basis vector matches the algebraic multiplicity of 1. And then you have the eigenvalue -2 corresponding to 2 eigenvectors and having algebraic multiplicity 2. So that's a situation where if you use your computer here, you could say, yes, I have a basis for R3 because I have 3 basis vectors there. Whereas the second one for part D, you get the eigenvalue -1, you get the same eigenvector 1, -2, 0. But then here you get an eigenspace of -2, you only have 1 basis vector. So then you only have 2 basis vectors in R3, so you don't have a basis for all of R3, even though the algebraic multiplicities all add up to 3. And then in the third case, you had distinct eigenvalues, so you already automatically knew that you had a basis of eigenvectors that span the whole space. So that's how you might use computer dot eigenvectors underscore right with the parentheses like that is how you do it. Okay, so that's how to do it with computers.